Okay. Coming to one more topic on functions in more than one variable, we have one more important topic, that is Jacobians. We use this extensively in multiple integrations, but then this is just an introduction to Jacobians here. So we look at the properties of Jacobians. What exactly is a Jacobian is just the partial derivatives. If suppose u and v are functions of x and y, use a function of x and y, and v is also a function of x and y. How do I find Jacobian of u and v with respect to x and y? Is just the partial derivatives of u with respect to x, with respect to y, v with respect to x, and v with respect to y. I take the determinant, something like AD minus BC format. I have A, B, C, D. It would be AD minus BC format. Okay. Yeah. Now coming to the first property of Jacobians, that is the chain rule kind. Okay. If I take J and J prime, what is J and J prime? If J is Jacobian of UV with respect to XY, then J prime would be Jacobian of XY with respect to UV. If I take the product of J and J prime, it turns out to be 1. And then there are examples with proofs. By the way, I use this property to find, in case if I am asked to find out J prime, if I am asked to find out J prime, I'll be doing J or J prime, whichever is easy, I will do first. And then from this rule, I'll be finding the other one. That would be what? J prime would be what? 1 by J, Jacobian. Okay. So, or if I want J, then it would be reciprocal of J prime. Okay. Like that I will use. Not exactly to prove. Usually questions will not be asked to prove J into J prime is equal to 1. There's one more very important property that is called the chain rule of Jacobians, where instead of directly applying Jacobians to functions which are dependent. See, UV are two functions which are in terms of R and S. Okay, and R and S are functions in terms of X and Y. Okay. In such a case, instead of directly writing the complicated complicated Jacobian, the determinant, I'll be splitting it as a chain rule where U and V with respect to R and S I will do, R and S I will do with respect to X and Y. Okay. This is an important property, guys. You tend to get problems on this in your exams. Okay. Also, there's one more important thing, that is if Jacobian turns to be 0, the functions for which I am finding out the Jacobians, they would be dependent. If Jacobians are Jacobian of two functions with respect to variables x and y, if I'm finding out, if it turns out to be 0, then those two functions are said to be functionally dependent. Otherwise, it's said to be independent. Means what? If Jacobian is non-zero, then the functions are said to be functionally independent. Okay. Yeah, they're dependent in one way or the other. You can just see in this example. Okay, where u is related with x and y, v is related with x and y as well. Okay, I here in this example, I would like to focus on the third property, the chain rule of Jacobians, to do this problem. That is what? I want the Jacobian of uv with respect to r and theta, where see here, u and v are functions in x and y, not r and theta. X and y are functions in r and theta. So accordingly, I'll find the Jacobians. That is what? U and v with respect to r and theta, I'll find out. R and theta, I'll find out with respect to x and y. Just multiply both of them together. Okay. So what I'll be getting is u r u theta, v r v theta. Okay. Yeah. U with respect to r. No, I'm sorry. I'm supposed to be finding out with respect to r and theta, but then u and v are in terms of x and y. Okay. So I'll be doing it. I'll be doing u and v with respect to x and y only. Okay. It is what? U with respect to x, u with respect to y, v with respect to x, and v with respect to y. U with respect to x, what will be x square minus y square? Y derivative with respect to x would be 0. X derivative would be x square I have, so it is 2x. And then uy would be what? Minus 2y. Vx would be what? 2y, because 2 and y are constants, x derivative is 1. Vy would be what? 2 and x are constants, y derivative would be 1. So I'll be having 2x into 1, which is 2x. Okay, I'll be finding out this value. Okay, so what would be this? This value would be AD minus BC kind, 4x squared minus of minus. AD minus minus of minus 4y squared. Okay, that's what I have got. Of course, I can write this as 4 into x squared plus y squared, guys. Okay. x squared plus y squared, I don't have anything here. Anyways, x squared plus y squared can be r squared, right? 4 into r squared. Okay, we know polar coordinates, right? There's one more Jacobian that I'm supposed to be finding out. That is my dou x comma y with respect to r and theta. Okay, so thus that would be what? XR, x theta. That means what? X with respect to r, x with respect to theta. Derivative of x with respect to r and with respect to theta. Y with respect, derivative of y with respect to r and y with respect to theta. Look at x and y, guys. They are functions in r and theta. So x with respect to r derivative would be 1. So I'll be having cos theta. Okay. X theta derivative, cos theta derivative would be what? Minus sine theta. So r is a constant and minus sine theta is what I'll have. Y derivative with respect to r would be sine theta. And then sine theta derivative would be cos theta. Okay, so if I find the determinant, what would be the value? R into cos square theta. Minus of minus is plus r into sine squared theta. If I take r common, it's obvious that it is cos square theta plus sine square theta, which is 1. Okay, so this value would turn out to be r. Now what he has asked us is not this u comma v with respect to r and theta. So I'll be writing the chain rule here. That is what? Dou u by dou v. U and v are in terms of x and y, functions in x and y. X and y are in functions of r and theta. Okay, so there I've got dou u this thing, this first Jacobian to be 4r squared and the second Jacobian to be r. So this final value would turn out to be 4r cube. Okay, this is the answer. This is how I'll find Jacobians. Chain rule of Jacobians is very much important. Okay, and then if determinant turns out to be 0, the functions will have functional dependence. Okay.